Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the director of content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
Today, I wanted to talk a little bit about the idea of reaction rates. It's a notion that comes to us from an application of the mobile process calculi to modeling physical phenomena such as chemical reactions and biochemical reactions and biological processes in general. The semantics of modeling reaction rates in the process calculi end up getting kind of complicated. The idea is that the rates are associated with channels, and then you do a stochastic selection or just a probability distribution of selection of COM events based upon the reaction rates. I mean, it's kind of easy to code up, but getting the semantics compositional, on good sound footing is not trivial. Radu Mardari and Luca Cardelli came up with a version that's pretty good, and I would recommend that people take a look at it if they're interested in stochastic calculus.
Is the semantics that they wrote up, are they compositional?
Yes.
Oh, okay, cool.
Yeah, but it's pretty complicated.
All right.
So a few years ago, I had this thought fly by that with the Annihilation style reduction semantics that's available with the row calculus, I could design namespaces to give me whatever reaction rates I wanted. So essentially, the thought is that you have this kind of recursive reduction relation, and I'll make sense of that. But with the recursive reduction relation, you then at every recursion step, you're sort of calculating a notion of rate based upon that until you get all the way down to the ground, and then there's that's a unit. And from there, you can kind of design namespaces, because you have an infinite number of names associated with the infinite processes, and so you could design namespaces that give you whatever reaction rates you wanted. So let me actually walk through some examples here.
Yeah, so one thing I wanted to ask about this annihilation-based COM rule, it's totally different than the usual COM rule that we're talking about, right? The usual COM rule is not even a specific instance of this annihilation COM rule. Is that right?
The relationship is a little more nuanced and subtle. For those people who are listening, I have a set of slides we'll make available on the website. I'm staring at the first slide in the slide deck, and it addresses the notion of annihilation itself. And this is part of a more general idea that Milner put forward a long time ago, that if you had some kind of algebra on whatever your names are, then you could define some kind of relation, an abstract relation called channel co-channel. And then you could use that to determine when you get a reduction. If you have a for comprehension and an output that meet together on a channel co-channel pair, then you can get a reduction. And then the annihilation idea is just to supply a channel co-channel relation.
Okay, that makes sense. And just to clarify, when you say channel co-channel, you're just talking about source and target channel, right?
That's exactly right. That's
okay.
They're either ends of a communication channel.
Yeah.
One notion of annihilation, there are many, but one notion is you say that P annihilates Q, or they annihilate each other because it's a commutative relation. if there's any R that P par Q eventually reduce to, then that implies that R eventually gets to 0. Yeah. And what that means is that all paths out of P par Q eventually get to 0. That's the definition. Now, obviously, with this kind of quantification, you have to be careful if you're trying to think about it in terms of Levere theories or enriched Levere theories. And that's kind of why I throw this out there. I'm interested in testing Christian Williams and John Baez's notion of graph-enriched semantics. And stochasticity is one area where we need to check and see, does their method extend? And the other is this annihilation idea. And the annihilation idea in the context of stochasticity might give us a reconciliation between a normal notion of reduction and a stochastic notion of reduction. The thought is you have a new COM rule. Yeah. That says that if P annihilates Q, then if we hang a for comprehension off of the name of P or at P, and we hang a send off of at Q, then it reduces in the usual way. Now you might say, well, hang on a minute. The annihilation relation depends upon the definition of reduction, and now you've made reduction dependent upon annihilation. Does this circularity ground out? Do we ever get off the ground? And the first thing to note is that 0 annihilates 0. So if you put 0 in par with 0, that's equal to 0. And so all paths out of there get you to 0. So at a minimum, we have that 0 annihilates 0. And so we can then use at 0 as a channel for communication. So we have at least one channel. And now what I'll do is I'm going to design a namespace. I'm going to define a function from the natural numbers into processes. I'm going to define two such functions. So I'll call them P and negative P. And so P of 0 is just 0, and negative P of 0 is just 0. Mm-hmm. And then P of n is going to be the for comprehension that listens on the at of P of n minus 1 for y, and then does 0. Mm-hmm. Right, so we recurse down, and then forming a for comprehension on the one level down, the name of that. And then negative P of n is the dual of that. So we take at of negative P of n minus 1 and send 0 over that channel. Right. And it's an easy induction to prove that P of n annihilates negative P of n.
Yeah, it makes it really helpful that the continuation on P of n is just the stopped process, right? So they're always going to reduce to the stopped process. So that makes the annihilation really easy, I guess.
Yeah, that's correct. I mean, you can make it more sophisticated, but just for purposes of our discussion, that's
right.
And by the way, I wanted to mention something practical here before we take the next step, which is that we don't actually need the quantification, in the sense that in a practical setting, you could do what nature does. You could just let all these processes run kind of in superposition, and whichever co-channel pair got you down to 0 first, that would be the one you'd take, and that would be a way to break the race. And so if there are some that run forever, they don't give you good service, right? So they're not good co-channel pairs. And I'm using the word superposition deliberately because there is a way to give a kind of quantum mechanics style interpretation of, yeah, exactly. So you think of all these processes as potentially running, and then you use the quantum notion of probability amplitude to get the distribution over which you would do you would make a selection for the race.
Oh, interesting. Would treating it that way produce a similar distribution as to what we'll see later in the slides?
No, that's a very different world.
Cool. So, okay.
Yeah, I mean, like, and for the longest time, I mean, since about 2006, I finally realized that there's an interesting question about quantum mechanics in general, which is that like what proves that that notion of probability distribution is actually a notion of probability. We have an axiomatic formulation of probability, right? And then there's this interpretation of the physics that says, well, hey, when I whack a dual against an operator applied to a vector, that is in fact a probability amplitude. That interpretation, you need to go and check and see if that in fact does axiomatically satisfy the definition of probability. In fact, it doesn't. It's actually an alternative notion of probability. It's a notion of probability that's bigger, that includes negative probabilities. And I would argue that that's actually a better axiomatization of probability. And it's one that corresponds with our notion of what probability means in natural systems to a high degree of accuracy. So so that's why I'm saying it's actually pretty different than this stochastic notions that have been put forward by even the Mardari and Cardelli formulation. That notion of probability is not the same as the one you get from quantum mechanics. So that's why they're different. It's interesting.
So what would a negative probability mean?
It has to do with whether or not your probability amplitude is a complex number.
Yeah. Okay. Right.
And Scott Aronson has an interesting blog on exactly these points. It's a cool area to go and investigate. And you can lift, for the mathematicians in the crowd, you can lift a lot of this up to quaternions and octonions. So the same built-in notion of probability that you get from the complex numbers and the quantum mechanics interpretation, you can kind of rejigger or iterate the same construction with quaternions and octonions, and those are the only ones available. Those are the only three that fit that particular style or notion of probability. Yeah, it's crazy world. I really art is long, life is short. I really wish I had time to go and investigate this further because it's really fascinating. Back to reaction rates. We just designed a namespace, right? So the namespace kind of bifurcates into a sort of some input-based names and some output-based names. And as long as we always pair up inputs and outputs at the same level, then they annihilate each other. And so we now have an infinite set of co-channel pairs. And so now I want to turn our attention to what I was originally aiming to talk about, which is this idea of rates. If I just I'm looking at a slide in front of me now. I think it's slide 4 or 5, where I just look at a for comprehension in parallel with an output. I'm going to assign a cost to effecting the reduction at all. And we'll just call that R. And then I'm going to assign a cost to the transmission of data. And I'm just going to call that T. And then when I recurse, right, because in the annihilation style com rule, I have to go and check and see. So if I'm listening for Y from at P and I'm sending on at Q, I now have to go and check to see if they annihilate. Or we can assume that they annihilate, but I still have to go and do the cost of that.
Right, because they'll reduce, so we'll get some reaction rate from
that.
Q, right?
That's exactly right. So I do R plus P, so that's the single step reduction, whatever that is, together with the transmission cost times whatever it costs, whatever the rate is associated with P bar Q.
So when you're talking about the cost of transmission, what exactly are we talking about there? Are we talking about with sending this message on the channel Q, or what kind of transmission are we?
Yeah, that's right. So in particular, the only observable effect of sending the data across the channel is to plunk the data in with a substitution. Right. So it's essentially what we're measuring is the complexity of the substitution.
Right. Okay. Cool.
Right. So rather than a number, it would really be a function. But for purposes of our discussion, we can just approximate it as a number.
Okay.
So then the first thing to note is that if my source and target are p of n minus 1 and negative p of n minus 1, then what we would calculate is r plus t to the n.
Yeah.
Right, because that would bottom out. It would recurse and bottom out at p of 0 and negative p of 0. And so we'd just be multiplying r plus t n times if we start out at n minus 1. What we can see is that we're already hitting probability, right? Because I've now designed a namespace that provides rates that are governed by the binomial theorem.
Right.
And we didn't even break a sweat, right? It's like, it took us three lines to get there, even though I'm being a little bit fast and loose, and I'll say exactly where I'm being fast and loose in just a minute. The mathematics that we just went through is literally less than an order of magnitude of the complexity of the stochastic presentations. And yet I'm getting a notion of rates that clearly correspond to a notion of probability. And I want to just point out that we did a simple namespace design, but we could be a lot more creative in our namespace designs. That begs an interesting question, right? And that question is, how do we actually calculate that rate of p par r? Because there might be races in there. And the other thing is that there might be terms of the form dereference x. Right. So that's a legal process, and I haven't talked about how to calculate the rate of dereference x. Let me address the races idea first.
Before we go to that, I was wondering. So I remember from the row calculus paper that you had a notion of annihilation in there that was more general than this annihilation that you presented, because it wasn't that the processes eventually reduced to 0. It was that they reduced to some fixed process or something along those lines.
Yeah, you have to be super careful. They have to be special fixed processes.
Okay.
Otherwise, you don't get commutativity, and there's certain properties you have to go and check.
Okay, that makes sense.
Yeah.
Have you done a reaction rates for that type of annihilation as well?
No, I haven't.
Oh, okay.
I mean, it could be done, and further work. But it's a really good question. That's right. And I have a feeling that the requirements on the states that you get to in order to preserve certain properties are going to be closely related to the notion of probability that you end up with.
Yeah.
So that's an interesting math there as well. But on to this idea of races. So let's define the down arrow p, or just down p, to be the predicate that there's a q that p reduces to. Yeah. So you can find some q that p reduces to. And then we can define races of p to be all the triples, L, R, and T, such that p is structurally equivalent to the par of L, R, T, and some S, and that either L reduces with T or R reduces with T, but not both. So they're in conflict. So it's a real honest to God race, and you can only go one direction or the other.
Yeah, that makes sense.
Yeah. So then you just collect all those triples, right?
Yeah.
And you could recursively do this, but we're just taking the first level. So what we'll do to calculate P par Q is to take a normalized sum over the races. That's the idea. So we sum up the rate for L par T and the rate for R par T, and then we divide through by some weighted measure of the set races par Q. There's some wiggle room in terms of how you weight that. You could just take its cardinality, which is what I've done on the slide, but you could do some other things as well. For the mathematicians, it might be interesting to go and play with that and see what different weights give you. And then what we'll do is we'll just neglect any contribution from the dereferences. We just simply say they don't contribute to the rate, because unless there's a substitution, they're inert, and we cover the substitution from the transmission contribution. So it can be safely neglected.
Right. So you're saying if one of these LRT terms is some dereference name, then we can just kind of forget about it.
Well, I'm just saying that in a par, if in like, so we'll sift the par into races and these other things,
Yeah.
these,
Okay.
right? And the other things contribute nothing.
Yeah. Right. Okay.
Now our definition covers all the possibilities. We've given a well defined function from processes to numbers. and that gives us more than enough room to go and design namespaces that provide a whatever kind of distribution you'd like to see. It's a different way of thinking. It's a different way of programming, and that's kind of important. But this is what I've been trying to argue for a long time: is that people should think about the opportunities of designing their namespaces to get the kind of computation they want. This works from the point of view of security. It works from the point of view of sharding. And now it also, I'm arguing, it works for designing it if you wanted to include a notion of rates. And just to make contact with RChain, the whole idea of having phlogiston controlled reduction is literally giving a rate to reduction. And there's this direct correlation between cost and compute.
Right.
If it costs more, it's gonna, in general, be slower to compute. So literally, we're RChain is a stochastic implementation of the row calculus. That's what it is, and that's neat because there are all these tools out there for doing simulations of stochastic processes. In particular, Andrew Phillips, like over 10 years ago, built the stochastic pi machine. And that has been used over the last decade to model chemical and biological phenomena. Andrew Phillips is now head of computational biology at Microsoft Research. In the slides, I reference a paper that came out like in 2009 or 10, where they look at a particular set of reactions that are related to MHC loading, which has to do with certain kinds of peptide production. Before I kind of go into a more complicated set of chemical equations, what I want to do is just give the schema here for people to understand. Imagine that you've got a chemical equation that's of the form reagent 1 plus reagent 2, reacts at a rate of K to produce a product.
Mm-hmm.
So if you want to interpret this in a pi-like calculus, we can actually kind of go through it compositionally. So we just use the normal double brackets. We put them around the entire equation. What we're going to say is that the left-hand side of the equation is going to reduce according to a rate in the stochastic version of the calculus to the product. And then we can recurse. So now we say that reagent 1 plus reagent 2 is going to be the meaning of that. The interpretation of that is going to be the interpretation of reagent 1 in par with the interpretation of reagent 2. So now we actually have a reduction. We have a red X expression. Potentially we have a red X expression. So so it's making sense, right? It's actually, we're able to give an expression in a form that lines up with the way the calculus reduces. In some sense, chemistry was always meant to be written in process calculus.
Yeah, it's interesting to think about the presence of two reagents in the same solution or what have you, just being two processes running in parallel with one another.
Yeah, and actually you get the notion of concentration, right? So if you have, it's not just two processes, it's however many. Yeah. So the idea of moles, right, corresponds to literally, multiplying that many copies of those processes, which again makes these kinds of simulation tools like SPIM really, really interesting, because now people can use these tools to model out validated behavior. Mm-hmm. Right, under these kinds of loads with these kinds of requests for these kinds of smart contracts, what are we going to see? You can think of those as big chemical soups, and you can write down those solutions and get simulations. So we have literally off-the-shelf tools that are available for our chain that you can get from other other research projects that were using them for something entirely different, and apply them to modeling out validator economics.
Yeah, that's pretty incredible. So you can like set up a ton of different scenarios and just test them all out and make sure we get the expected behavior in each one of them.
That's exactly right. Or you can determine that you're going to get some anomalous behavior. Oh, look here, we get a spike in the concentration of this contract. Well, that's interesting. Around Christmas time, we start to see these kinds of perturbative behaviors, and which then take the thing into a different equilibrium.
Yeah.
We can import the tools, but we can go further than that. We can say, hey, this biological process, this immunological response, this neurological response, kinetic proofreading, these kinds of biological things which we know have specific functions, can be imported into the designs of our smart contracts.
Yeah, that's so cool.
Yeah, I mean, to me, this is sort of why I keep saying we should be copying nature. We should be copying nature. We should be copying nature, right? But now I'm saying, and we can copy nature. It's not us just sitting down with a sketchbook and sketching what we see. We can make this a lot more precise, a lot more specific. So I mean, so just to put some flesh on the bones here a little bit. Probably everyone knows that if you take some sodium and some chloride in equal parts, they react to form salt, NaCl. And so now we can interpret this, right? So the interpretation is that the process that represents sodium in par with the process that represents chlorine becomes the process that represents sodium chloride. And now the question is, what would be a process that represents sodium? Well, sodium has one valence electron. It wants to give away an electron, whereas chlorine would very much like to have an electron. So you can actually take it a step further. You can model this behavior of electron sharing. So you say you make a new scope which represents the electron, and then you have sodium sending on a channel and chlorine receiving on the same channel that electron. The bond between them could just be the new scope, or it could be that they keep sort of sharing the electrons. So in the next step, the chlorine sends it back to sodium, and sodium receives it, and then sodium sends it back to chlorine, and that would represent your sharing behavior. So you can actually get a fairly detailed picture of the information flow that's associated with the nuclear chemistry in terms of the process language. So I think that's really cool.
I agree. So the electron is the message that they're passing back and forth between each other?
That's exactly right. And it's covered by a new scope. So it's a piece of data that the new scope represents a kind of bonding. And in fact, one of the things that I did was to model Michaelis-Menten that way. So Michaelis-Menten is this, it's an interesting reaction schemata where you have a reagent and a catalyst, and the catalyst promotes the reagent to a new state. But before it does this promotion, they end up in a particular kind of bonded pair where the bond can dissolve. So they can go back to just being reagent and catalyst, or you can go forward to the promoted state. If you chain these Michaelis-Menten reactions together, it becomes the basis for something called kinetic proofreading, which allows you to convert energy to signal fidelity. And so I did a pi calculus analysis of Michaelis-Menten. But the twist on that analysis that I did, the people who pioneered this work were Bill Silverman and Ehudi Shapiro and Regev, Aviv, and Cardelli and Andrew Phillips. So that was sort of some of the prominent members of the crowd. But they weren't looking at the logical perspective. So my argument was that while it's interesting to model process behavior, I think it's more interesting to look at it in terms of spatial behavioral types. You could write down a formula a logical formula, which represent, and here you use the spatial formula combiner for the par, right? So you have par of two formulae, but then the evolves to becomes implies eventually blah. You can do the same kind of compositional interpretation of the chemical equations, but to get logical formulae that processes then satisfy.
Yeah.
And then you can turn something like Michaelis-Menten into a scheme, and you can go and check to see if certain systems of equations are Michaelis-Menten mechanisms.
Interesting.
So you get so it becomes a classification mechanism. So if I go back to this the situation that was from this paper I was mentioning, so there's this fairly complicated biological process that has to do with the formation of a peptide loading complex, and it's easier just to look at the picture in the slides. There's a collection of chemical equations that describe this system. They're non-trivial, but they still fit on a page, and those equations can be directly encoded in the SPIM language, which is just one syntactic generation away from Rolang. So where they have let and then process name equal and then a process body, instead of writing let, we write contract. Mm-hmm. And where they have do or, that's our select statement. And then the rest of it is they have outputs and they have inputs, just like we do. We write for comprehensions slightly different than the way they write their inputs. But by and large, if you look at the SPIM language, you can see the Rolang syntax in there. It's not a big stretch to grab that. So we can kind of do two things. One, we could import their biological descriptions over into Rolang, which would enable us to sort of import the growing body of knowledge of biological systems. But we could also look at it at the type level. So we do a behavioral type description of this and then go and check to see, hey, is this collection, this gaggle of smart contracts I wrote, is that a Michaelis-Menten style system? In other words, does it learn signal fidelity?
Yeah.
That would be a really interesting question to ask of smart contracts that are evolving in the wild.
Yeah.
So that's kind of I think that's a cool thing. But then the final point I wanted to make is that the methodology is different. The two overlap in the sense that the argument is that you would go to experimental data to derive rates empirically, right? So mm-hmm. You pour some stuff in beakers and you do multiple experiments and get a kind of a sense of the rates at which various things react. So you derive those empirically, and then there are two approaches. Either you can do this sort of stochastic formula where you get a probability distribution over the COM events that respects the rates, or you program a namespace that would give you those rates. And those are two different ways of thinking about it. And programming a namespace is a different way of thinking about the world. But from what I've seen, the RChain community loves this kind of programming mind twist, this kind of brain game. So I think it might be of interest to that community. The idea is that it's an interesting range of ideas, right? We're going from the theoretical out to the very, very edges of what a good notion of probability is, down to can we use these tools which were originally conceived for simulating biological systems to simulate RChain deployments, and to this other idea of maybe we can begin to learn from life. If we can import these biological processes into the system, well, maybe there's something that these biological processes do, such as an immunological defense response that might turn into a good security mechanism. Mm-hmm. And now we've got the tools together to be able to do that.
Yeah, I just think it's really cool how all of these different pieces are coming together. I definitely didn't realize the full scope of we need to model nature and, do as nature does and be compositional. I definitely didn't see how far that analogy actually went. But now that I'm seeing we can treat all of the behavior, validator behavior on our chain as some kind of biological system that's governed by certain laws, or some kind of chemical system that's governed by certain reaction rates. And that's really cool.
Well, I think it's cool, but I also think it's kind of necessary, right? Like the one thing that we can see over and over and over again is that our attempts to scale, whether it's a large scale agriculture or large scale manufacturing, something is amiss, something off. Whereas when we look at nature, and nature's seems to just scale gracefully.
Yeah.
Up in the Pacific Northwest, it's so lush and so beautiful at this time of year. And I wander amongst the trees and I go, look, there's no king tree directing all of this.
Yeah, well, and in fact, they're all in concert with one another, right? They all communicate with each other.
That's exactly right. And the more we learn about the network of communication amongst the trees, the more astonished we are. They use the mycelial layer to communicate with each other.
Right.
And they actually share resources. And when a tree is distressed, other trees will send it resources via this mycelial network. It's crazy distribution system it is. And so there's just something really awe-inspiring about the way nature scales. And, so I would like to make it very practical to copy nature.
Right. Like why reinvent the wheel when we already have the best example of a decentralized distributive system, available to us? Let's just mimic that.
Exactly. That's exactly right. And a part of good mimicry is just like figuring out what it actually is that we're mimicking, right?
Yeah, right.
This goes back to flight, right? People look up at the sky and they see birds flying and they go, we should be able to do that.
Yeah.
Putting these tools together is sort of a Wilbur and Orville Wright kind of effort.